Welcome to part 1 of our tutorial on diode rectifier circuits. Okay, so rectifiers, as we can say over here, stands for certain electronic circuits that can convert an AC voltage or power into DC voltage or power. So this type of circuits find much of an application in case of power electronics and in various power supply circuits as employed in various applications. So the process of converting an AC voltage into a DC voltage is termed as rectification. Okay, and now for rectification we can design certain rectifier circuits using diodes. Okay, so basically there are three types of the rectifier circuits that we can construct using diodes. Okay, so these are the number one comes the half wave rectifier circuit, and number two we have the full wave rectifier circuit, and number three we have the bridge rectifier circuit. So primarily in this tutorial we'll discuss about the half wave and the full wave rectifier circuits, and for a discussion on the bridge rectifier circuit please follow the part 2 of our tutorial on diode rectifier circuits. Okay, so having said that, let's just move on to the characteristics of a half wave rectifier. Okay, so here we have the half wave rectifier circuit. All right, okay, so that's it. So if you just take a closer look and I draw a circuit using a diode with a series resistance, which is referred to as the load resistance, which is in series with this diode, let's say I name it as D. So over here we connect at these two terminals, we connect an AC source voltage, okay, an AC voltage source which supplies the input AC voltage to this rectifier circuit. Okay, let me just change the color a bit. Okay, fine. Now this terminal, let it be called terminal 1, or rather terminal A, and this be called the terminal B. Okay, and we obtain the voltage output across the load resistance, as you can see here. So for an input AC voltage applied across terminals A and B, now the AC voltage being sinusoidal in nature, we see that it keeps on varying in polarity after every half cycle. So based on that data, we just go for the first half cycle in the beginning. So for the first half cycle we can see that the voltage in the input voltage waveform is on the positive side of the voltage levels. So the terminal A will have a positive voltage polarity, while that of terminal B will be negative. So the diode D, having a positive voltage on its anode, becomes forward biased and begins to conduct a current I through the load resistance and back to the AC source through the terminal B. Okay, so now since the current flows through the load resistance RL, it generates a voltage output during the first half cycle that has the same polarity of the input AC voltages polarity over here. So as you can see here, so therefore if we just draw the output graph over here, so these are the divisions for all the half cycles that I'm going to draw in this graph. So this is the time axis in both the cases, and here is the V output. Okay, so for the first half cycle, as we can see here, there is a voltage output generated from the rectifier circuit, which it varies in direct proportion with that of the input half cycle, and so we have an exact replica of the input half cycle at the output of the half wave rectifier across the load resistance. Okay, now when the second half cycle arrives, as we know that AC voltages just keep on varying in polarity after each half cycle. So when the second half cycle arrives, the polarity at terminal A is negative and that across terminal B is positive. So in this case we see that the diode D has a negative voltage on its anode, and therefore it's reverse biased, and due to the diode D being reverse biased, there is no current flow through the load resistance in this case. And let me just rub out what happens in case of the first half cycle. Okay, So since we're discussing the effects of the second half cycle, so in case of the second half cycle, there is no current flow through the load resistance RL, and hence there is no output voltage generated across the load resistance in case of the second half cycle. So in case of the second half cycle, we have zero output voltage. So now just moving on to the output graph again, we can see here the third half cycle is the same as the first half cycle, and hence the effects will be the same as that happens in case of the first half cycle. So we'll have again a similar output voltage that varies in direct proportion with this half cycle over here, I mean with the third half cycle, and we have an exact replica of the third half cycle at this point. And similarly at the fourth half cycle, which is the same as the second one, we'll have no output voltage. So that being said, this is pretty much the output voltage that we obtain for a half-wave rectifier circuit. So now if we just focus on the type of practical half-wave rectifier circuit, then we do not have any kind of theoretical voltage source as discussed over here earlier. So instead of a theoretical voltage source, we have a transformer. Okay, so we have a transformer on the contrary, to which we have the transformer's secondary terminal connected to terminals A and B, while the primary terminal of the transformer is connected to the AC mains voltage. Okay, now the AC mains voltage keeps on varying from country to country. At some countries it's to 20 volts, while in the Western countries it's 110 volts AC. Okay, in other countries, depending upon the standards, this value keeps on changing. So whatever it is, we apply the AC mains voltage at the primary coil of the transformer. Okay, now this transformer used here is termed as a step down transformer. Okay, since it just steps down, or rather brings down the voltage level from that available at the AC mains supply to somewhat a voltage level that doesn't damage the diode, and that is completely dependent upon the diode ratings, okay, as to what type of step down transformer we use. So in general, we use a step down transformer as said over here for constructing this circuit in practically. So now based on this, we know what happens in case of a rectifier circuit. And now let me just give you the mathematical the expressions that are required in order to calculate the output DC voltage, which is of course Vm by pi, where Vm is the peak voltage of the input AC signal, as I told you. And now when the diode D gets reverse biased, then the type of, or rather then the magnitude of input voltage Vi occurring across the diode gives you the PIV, or the peak inverse voltage, which is of course Vi in this case. And this rectifier circuit has a transformer utilization factor of about 0.287. So that means the circuit utilizes or rectifies about 28.7% of the total AC input power available at the terminals A and B. So having said that, let us go to the discussion on the full wave rectifier. Okay, so here we have the full wave rectifier circuit. All right, so in case of the full wave rectifier circuit, the circuit is a little bit different from that in case of the half wave rectifier. So here we have our transformer primary coil with the AC mains voltage. Okay, and then comes the secondary coil connected to two diodes this time, which is just contrary to of what we see in case of the half wave rectifier. And there is this load resistance across which we shall obtain our output voltage. Okay, the load resistance grounded one end, and the grounded end is connected with the transformer center tap. Now here I can say something, that the transformer, or rather the step down transformer used in case of a full wave rectifier circuit, is a center tap step down transformer. Okay, so the step down transformer is a little bit different from the two terminal transformer used here in case of the half wave rectifier circuit, in that it has three output terminals of its secondary. Okay, now the voltage at the secondary terminal of the step down transformer, I mean the center type step down transformer, is prefixed to 0 volts, that is the ground voltage. And now when an input AC voltage arrives at across the input terminals of this rectifier circuit, let's say this is Vi. So for the first half cycle, we see that the AC voltage lies in the positive voltage region, and hence the polarity occurring across, let's say, the terminals A and B will be somewhat like this. So terminal A will be at a higher voltage with respect to that of the center tap voltage, that's the ground voltage, while the terminal B will be at a voltage lower than that with respect to the center tap voltage. So the diode D1 in this case would be forward biased with a positive voltage on its anode, while diode 2 would be reverse biased with a negative voltage on its anode. So there will be a current flow through the load resistance and then back to the center tap terminal, and due to this current flow through the load resistance, there will be a output voltage generated with a polarity as shown in this diagram. So based on that, if we just draw the characteristics of the output, then we can see something like this. Okay, there goes the half cycle divisions. We'll have a half cycle output across the load or RL, the load resistance terminals. Okay, so here this half cycle is an exact replica of the positive half cycle as shown here in case of the input AC voltage. Okay, so in this case, as we can see here, we obtain a half cycle for the positive input AC half cycle. Okay, so let's say in case of the second half cycle, when it arrives, we can see that the second half cycle is reverse in polarity to that of the first half cycle. So let me just rub out what happens in case of the first half cycle. Okay, all right, that's pretty much done. Okay, so that's it. So for the second half cycle, as you see here, that the polarity across the terminal A becomes reverse to that what happened before. Now the terminal A has a reverse polarity or a negative polarity with respect to terminal B, which is obviously at a higher polarity than compared to the terminal A. So now the terminal B is at a higher potential compared to that of the center tap voltage, and that the terminal A has a comparatively lower potential compared to that of the center tap voltage. Okay, so now due to that, the diode D2 having a positive voltage on its anode becomes forward biased and begins to conduct, while diode D1 remains reverse biased and doesn't conduct at all during this half cycle. So there is a current flow through the diode D2, and then it goes through RL, that's the load resistance, causing an output voltage of VO across RL, and which is also of the same polarity of that happened in case of the first half cycle as shown here. Okay, so that's pretty interesting. So now the current flows through this path, I mean through the load resistance, and then finally returns through to the center tap again. So based on this conclusion, the output voltage waveform that we'll obtain over here would obviously be of the same type of waveform as that obtained in case of the first half cycle, as this second half cycle just gets inverted, and we get just the inverted replica of the second half cycle of the input AC voltage. Okay, so for the rest of the half cycles of the AC input voltage, the similar things will happen, and we shall get a pulsating DC output that just looks somewhat like this. Okay, so let's move on to the mathematical parameters over here. So the output DC voltage for a half wave rectifier would be 2 times that obtained across in case of the half wave rectifier. Okay, that's Vm by pi, and it's 2 Vm by pi, that's just a double. Okay, and now if you just assume that when any one of the diodes get reverse biased, a voltage of Vi, a reverse voltage of Vi falls across the transformer, a center tap and one of its ends, then that reverse voltage is regarded as the peak inverse voltage of the full wave rectifier circuits. So here we can say the PIV is nothing but Vi, which is just half of that in case of the half wave rectifier. Okay, so we can see here in two ways the circuit is already superior to that of the half wave rectifier, and now this rectifier, the full wave rectifier, has a transformer utilization factor of about 0.693, which is more than that in case of the half wave rectifier, which was about 0.287. So the full wave rectifier utilizes about rectifies about 69.3% of the total input AC power available across its terminals A and B, and it sends it to the output. So we can see that in case of these three specifications, the full wave rectifier is much more superior compared to the half wave rectifier in operation, and as a result we can regard that the full wave rectifier efficiency is greater than that of the half wave rectifier circuit. Now that's our conclusion from this discussion over here on half wave rectifiers and full wave rectifiers. So based on that, we come to the end of the tutorial, having said all that, and for a discussion upon bridge rectifiers, please refer to our tutorial part 2 of the diode rectifier circuits. Till then, it's goodbye and thank you.